Today we're going to look at geometric series. So we're going to look at both finite and infinite geometric sums and series. So just as a reminder, a finite one is when we know how many terms we're summing up. So we're summing up from the first term to the 12th term, or the 50th term to the 100th term. And an infinite geometric series or geometric sum is going to sum up from the first term all the way to infinity. I know, sounds impossible, but that's our objective today, the impossible. So, first of all, a geometric series is the expression of the sum of the terms of a geometric sequence. It's given by this lovely formula, S is equal to AF times the quantity 1 minus r to the n over 1 minus r. And I have the little disclaimer here that r, that common ratio, can't be 1. Well, if it's 1, it's not really a geometric per se. It's more of a constant sequence because it would be like 5 and then 5 and then 5 and then a 5 because you're just multiplying by 1. See how there's not actually a change? It's like a little hazy ground on whether it's geometric or not, because while it does have a constant ratio between consecutive terms, is it really geometric because it's constant and it's a little just fuzzy. Couple of things to label this AF. Go. That's my first term. R is that common ratio. And n is the number of terms. Also, point of reference, if r is 1, then I'd have all sorts of shenanigans because I would have 0 over 0, and nobody wants that. At least not till you get to calculus. Then it's a very interesting conversation. So, where on earth would this formula come from? Well, right? That's what one might ask. So, let's write the formula. So, geometric sum is really just a1 plus a2, or say 3 plus dot 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 all the way to an. Well, it's really a1 plus a1 times r, because that's really what the second term is that I've multiplied once by r. And then the next one is ar squared plus dot 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 all the way to a1 r to the n, that minus 1. I apologize, that was really bad looking r. Where am I spacing? Oh, there it is. Okay. So, and I'm just going to switch these over. That's what S is equal to. Well, I could also have an R times S, and that would be A1 times R plus A1 times R squared plus A1 squared cubed plus A1 R n minus 1 plus A1 So I have these two equations, and the blue equation is just if I took the red equation above it and multiplied by r. I added a few extra terms, but when I was writing it out, but it's the same equation, it's just multiplied by r. What I'm going to do is I'm going to take these two equations and I'm going to subtract them, because if I take two things that are equal and subtract them, I will end up with things that are equal as well. So this is going to be s minus rs on the left-hand side. And I'm going to have a1 minus a1r plus a1r minus a1r squared plus a1r squared. You see what's happening? This one and this one cancel. This one and this one cancel. This one and one of the ones in there. And a bunch of stuff cancel there. And then a1r to the n minus 1 and this a1r to the n minus 1 cancel. So these are all canceling. And we're left with minus a1r to the n. So S minus rs is a1 minus a1r to the n. Now on this left-hand side, I can factor out an s out of those two pieces. Oh, 1 minus r. And on the right-hand side, I can factor out an a1, and I'll be left with 1 minus r to the n. Divide both sides by 1 minus r. And we have s is a1 times 1 minus r to the n over 1 minus r. Ta-da! That is the sum of the first n terms. Crazy, right? Same thing we had here. Fantastic. So notice here, we don't have the last term, so I don't need to know what that I just need to know how many terms I'm summing up. So here I have a series. I want to sum up the first 9 terms of that series. So I need my a1. I need to have my r, and I need my n. My n is going to be 9 here. I have negative 2, then negative 6, then negative 18. I'm multiplying by 3 each time. So AF 1 minus r to the that's our formula. Negative 2, 1 minus 3 to the sometimes, depending on what numbers we have, they can get fairly large pretty quickly, and that was true about the terms of a geometric sequence, so adding up all of those terms should get fairly big fairly quickly as well. And 1 minus 3 is negative 2. At that point, I kind of cross those two out because they're the same, so why multiply by negative 2 to have to divide by it? So the sum of the first 9 terms, which I could denote as S9 like that, is negative 19,692. Oh. I can also write these geometric sums in sigma notation. Notice here it's starting at n equals 1 to 10, and I have 4 times negative 3 to the n minus 1. So my r is negative 3. My first term is indicated by that I'm starting at a1 right there. If I put 1 into that sequence for n, it comes out as a positive 4. And the total number of terms that I'm summing up is 10. In this problem, I'm going from my first term to the 10th term, which is 10 terms in total. So I write out my key for all the pieces that I know, and then writing down the formula. Good habit to write down the formula. In a scenario, if you have to memorize the formula, the more times you read it, the better you'll know it. Now this one's a little tricky with that negative, and this is probably the most common mistake on here, and I'm going to highlight it right now, is right here. Okay? So most people see those double negatives, they want to cancel them out and make it a positive. However, order of operations applies here. Applies always, but it applies especially here because that exponent has to happen first. When I raise that negative 3 to an even exponent, like I am here, it's going to come out positive. So those negatives are not going to cancel each other out. Okay, they do on the bottom, but this ends up still as 1 minus 59,000, sorry, and 49 over those become plus. If those cancel again, that doesn't always happen, just because it happened twice in a row. It's more of a coincidence. Negative 59,048. Take a minute, pause the video. First, hold on. Notice that there's something different first. Okay? Notice it, observe. And it's not just that I used K instead of N in this problem. The fact that I use K instead has no real bearing on it other than some textbooks like other letters. So common ones you see are N, K, J, and sometimes you even see some textbooks use I for index of summation. I'm not a fan of it personally, but it is a possibility. So pause the video, try this problem, and then we'll take a look at it together. Did you try the problem? All right, I'm trusting you on that. So first of all, my common ratio is 1/2. My first term is not a 1 in this scenario, it's a 10 because of this bottom piece. So I've got to plug in 10 into my K to find out what that first value is. When I do that, it comes out as 1/2 as well. So we're starting at 1/2. This is really saying 1/2 plus 1/4 plus 1/8 all the way to whatever the 20th term is. Now, tricky thing, is n this top number? No, it is not. Just like with our arithmetic series, we're talking about the 10th term plus the 11th term plus the 12th term plus the 13th term plus the 14th term, 15th term, 16th term, 17th term, 18th term, 19th term, 20th term, which is 11 terms in total. Okay, count on your fingers as I went through those. And again, you can do 20 minus 10 and then add 1 back in because subtraction is just running in between. So our sum here, notice I'm not going to put a subscript on this sum because it's not starting at the first term to go to the 20th. It's starting at the 10th term. So I'm just going to call it generically S. S is 1/2 for that starting value. 1 minus 1/2 to the 11th over 1 minus 1/2. So 1 minus 1/2 to the 11th is 0.99. I just rounded to 4 decimal places. That decimal does continue going on a little bit further. Okay, 4 is good enough. Which is the 10,000th place for those who are being more precise in their language. So, there's a story about the origin of chess that goes something like this. When the inventor of the game showed it to the new emperor of India, the emperor was so impressed by the new game, he said to the man, "Name your reward." The man responded, "Oh, Emperor, my wishes are simple. I only wish for this. Give me 1 grain of rice for the first square of the chessboard, 2 grains for the next square, 4 grains for the next, 8 for the next, and so on for all 64 squares, with each square having double the number of grains as the square before." The emperor agreed, amazed that the man had asked for such a small reward, or so he thought. Okay, so we all see how this is going to be in geometric sum because you're adding up, it's doubling each time, and you're going to be adding it up to find the total amount of rice that he asked for. So the first question is, how many grains of rice would be in the first row of 8 squares? So when we're looking at, and that's the next question, when we're looking at the first row of 8 squares, well, the first square had 1, and it's doubling each time, so I'm multiplying by 2 to the 8th over 1 minus 2. So 2 to the 8th is 256. So you have 1 over negative 255 over negative 1. So that's 255 grains of rice in the first 8 squares. Now, the follow-up question is, how many are on the entire chessboard? Well, instead of just the first 8 squares, I want the sum of 64 squares total. 1 minus 2 to the 64th. And so 1 minus 2 to the 64th, however, is negative 1.844 times 10 to the 19th. Negative 1. So my sum is 1.844. I should to the 10,000th and last one. So 7 times 10 to the 19 grains of sand. Not sand, of rice. Just a bit. Oh, follow-up. If I wanted to write this in sigma notation, this particular problem, okay, would be the sum from the first square to the 64th square of the explicit formula, 1 times 2 to the n minus 1. You don't really need the 1 in front of it, but just follow up. Carla's clothing shop opened 20 years ago. Good, that's nice. The first year she made $3,000 in profit. Each year thereafter, her profits averaged 28% greater than the previous year. 28% greater. When I write my R, it's not going to be 0.28. It's going to be 1.28. Because I want to have all the profits she had the previous year and then that increase on top of it. So that's really 1 plus 0.28, which is 1.28. How much profit did Carla earn during her 18th year of business? Now, this is asking just that 18th year. So this is looking for a sequence, okay? So just, or a single term, rather than the sum of all 18. So the single term in that 18th, her first year she had 3,000, the common ratio is 1.28 to the n minus 1, so 18 minus 1. So really 3,000 times 1.28 to the 17th, which 199,384.20. Pretty impressive. What was the total amount of profit that Carla earned over the first 18 years? So over all 18 years, that's going for a series or the sum of the terms. Okay, and this is where I'm going to have S, and I could call this S18 if I wanted, because I'm starting from the first term, but I don't really need to. 3,000 for that first term, 1 minus 1.28 to the 18th, over 1 minus 1.28. 3,000. I'm going to actually calculate. Sorry about that. So when I need to do this, I'm going to do 1 minus 1.28 to the 18th. And I'm going to multiply that by 3,000 and divide by 0.28. Notice I'm using the answer function here a lot. So what that tells me is over the 18 years. Okay. All right. Little Jack Horner baked a pie and promptly ate half of it. Wow. I hope he didn't have a stomachache. Determined to make the pie last, he decided then to eat only 1/2 of the pie that remained each day. Record the amount of pie eaten each day for the first 7 days. So that's a sequence. It's how much did he eat? So he, on that particular day, so it'd be like 1/2. Next day he ate 1/4 of the pie, 1/8, a 16th, 32nd, 64th. Oh, sorry. And last one, 1/28. each of those 7 days, record the total amount of pie eaten since it was baked. So I'm going to switch over. So again, oh, this was half. So he's eaten half of the pie. He eats another quarter of it on Monday. So by that point, he's eaten 3/4 of the pie. So here, that top row is the sequence, and the second row is the partial sums. Second, 165, 128. So then by Tuesday, he's had 7/8 of the pie. Wednesday, he's had 15/16 of the pie. Thursday, he's had 31/32 of the pie. Friday, he's had 63/64 of the pie. And by Saturday, he's had 127/128 of the pie. So he's had most of that pie, and it's starting to get really stale and not that delicious anymore. He's eating crumbs by the end. Okay. So, well, think about it. A slice that's 128th of it. The normal pie is cut into 8 pieces. Take each of those 8 and cut it into 8 again, and then cut those all in half. So yeah, no, really, really small. If Jack lives forever, then how much of this pie will he eat? Okay, so at a certain point, it's probably going to give him food poisoning, and there's going to be a certain point where he's just cutting crumbs in half and can't cut things in half any smaller. So a physicist would say he eats the whole pie. A mathematician is going to say, well, he's approaching eating that entire pie. Do we agree with that? I hope so, because I have no feedback for you to tell me you don't agree. So I'm just going to move on. So what this is talking about is the difference between what's called a convergent series. It's a series that approaches a long-term value as the number of terms increases, or a limit, right? We've talked about how long-term value is talking about a limit. And a divergent series, more than just a book series, but a series that does not approach a long-term value as the number of terms increases. So you can have a series that's either going to converge, where it approaches a sum, or diverge, where it doesn't. So if a geometric sequence converges, and that will only happen when the absolute value of r is less than 1, then the sum of that infinite geometric sequence is AF times 1 minus r. AF divided by 1 minus r. I apologize. That is such an easy looking formula. So let's go back to little Jack Horner, who sat in a corner eating his pie infinitely long. So on the first day, and I'm going to go back to that sum, right? Infinite sum is AF over 1 minus r. On that first day, he ate half of the pie and decided to make it last. He only ate half of each remaining day. So half over 1 minus a half is another half, which comes out as 1. He ate the whole pie. He's approaching eating the whole pie, which we basically could see in this table. You could see that this table of partial sums, these are what's called partial sums because they're finite sums, is getting closer and closer and closer to 1. And that's what a convergent series is that as I tally up more and more of these values, I'm going to approach a value instead of getting infinitely bigger. Something that would be divergent would be like if I had that on the first day he ate 1/8 of the pie, and then each day he ate twice as much. So 1/8 plus 1/4 plus 1/2 plus, and then because right there you're at 1 already. So it's going to keep getting bigger and bigger and bigger. That would diverge. Whereas this one where I had 1/2 plus 1/4 plus 1/8 plus 1/16 plus dot 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 forever is going to approach 1. Pretty cool, huh? So here is an infinite geometric series. I know it's infinite because I've got this lovely dot 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 on the end, and I don't have a stopping point. It's not saying sum up the first 10 terms or anything. So my AF is 9, my first term. My R is a third, because between consecutive terms, that's what I'm multiplying by. And again, our easy formula is just AF over 1 minus R. So It's going to be AF of 9 over 1 minus 1/3, which is 9 over 2/3. Oh, sorry, which is 27. And we like to put a little infinity subscript on it. So what that's saying is 9 plus 3 plus 1 plus 1/3. I'm going to type in a bunch first to start. Okay. Should come out as 13.5. That's what 27 halves is. I'm at 13 1/3 already. Plus 1/9 plus 1/27 plus 1 over 81 plus 1 over 243. And you see how while I'm increasing by a smaller amount, and you can see us approaching that value. And again, infinite geometric series will only converge if absolute value of r is less than 1. That's really saying, in other words, that, oh, not crayon, goodness gracious. The absolute value of r is less than 1, saying that r is stuck between -1 and +1. And that makes sense, because the only way to add up infinitely many things is if they're getting smaller, not bigger. If they're getting bigger, I wouldn't be able to add them all up. We can do infinite sums in sigma notation. Notice here that in sigma notation, I have a lovely infinity sign on the top. That's the only difference. So I'm going to have my s infinity. My first term here, if I put in that 1, I can see my first term is 8 over 1 minus 1/2. 8 over 1/2, which is 16. I know. Probably loving this formula. I do. I think it's awesome. All right, so pause the video and try this problem. So my first term is 15. I have a common ratio of 2/7. 15 over 1 minus 2/7. 15 over 5/7, which comes out as 21. Go ahead, pause the video and try this one. Did you try it? All right. So my AF is 81. My common ratio is 5/3, and I can't sum it up. This would be an example of divergence. And it diverges because 5/3 is bigger than 1. Trick question. Hope I didn't fool you. Oh, this question. I love this question. Show that 0.9 repeating is equal to 1. Yeah, right? 0.9 repeating. So 0.9 repeating, and there are a lot of different ways to show this. I could show this using fractions. I could show this using from a philosophical point of view. I can show this by saying, what's the number in between them. There's a ton of ways. Since we're talking today about geometric series, specifically finite and infinite series, I'm going to use geometric series to show this. I hope, though, you took a moment to pause the video and actually think about this and try it on your own, because it's always a great discussion tool. So 0.999 repeating. That's really 0.9 plus 0.09 plus 0.009 forever. Well, what's my first term there? Well, my first term is 0.9. My common ratio is 1/10. So when I use my infinite sum formula, I'm talking about the sum of these is going to be 0.9 over 1 minus 1/10, which is 0.9 over 0.9, which is equal to 1. Boom. Pretty cool, huh? All right. Just like everything else, we can have application problems. This is an application that doesn't spark a lot of controversy. But when Super Balls sprang up on the scene in the 1960s, kids across the United States were amazed that these hard rubber balls could bounce to 75% of of the height from which they were dropped. If a super ball is dropped from a height of 10 feet, how far does it travel until it stops moving? So, since I don't have an endpoint, and we're going to continue to assume that it's going to keep bouncing forever and ever and ever, and again, in reality, it's going to hit a wall somewhere or hit a corner and not be able to go any further, but we're going to say we're working in some sort of unlimited space. Okay, I have that AF is equal to 10. My R is 0.75. And then you would kind of jump right to this. 10 over 1 minus 0.75. And that's going to be 0.25. And that'll be 40. But wait, there's more. This is not done. Okay? So let's think about the path that a bouncy ball would actually take. So here's my ball. It's dropped from 10 feet. Okay? So it's dropped, and it goes back up, and it drops, and goes back up, and it drops, and goes back up, drops. Okay. So what we have found so far, we're actually this distance, plus this distance, plus this distance, plus this distance, plus this one, so on and so forth. I have neglected this upward distance, this upward distance, this upward distance. Oh, gasp. So there's a couple of ways we can figure out how much that is. I'm usually a fan of just doing another infinite sum, but some people just double this number and then subtract something else. It's fine. There's a lot of different ways to do it. So if this is 10 that's going down times 0.75 will be 7.5 for this next term. So infinite, so this was, I'm going to write next to it downward, okay? And so when I want to find the upward, it's going to be 7.5 is the first term over 1 minus 0.75. So 7.5 over 0.25 comes out as 30. So the ball is actually headed 40 feet, right? Yeah, 40 feet downward and 30 feet upward. So 40 feet and 30 feet is a total of 70 feet. And I have a nice little animated boom, 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 boom. So there's the ball going up and down, up and down, up and down, up and down. Okay. And this concludes our lesson on geometric series. Please let me know if you have any questions. And have a wonderful afternoon.